Assalamualaikum and good day. So this is the second part of topic 4 on the biocatalyst reaction. So in this second part, we are going to look at on the mechanistic models for simple enzyme kinetics. So you can refer this subtopic in the textbook Schuler and Carnegie, in chapter 3 on the enzymes. Okay, let's take a look on what is enzyme kinetics. So the enzyme kinetics, it refers to the quantitative analysis of all factors that able to determine the catalytic potential or the reaction of the enzyme. So for the enzyme activity itself, it represents the maximum. You have to look at the maximum catalytic potential of the enzyme, which will reflect the rate of the reaction in the enzyme catalyst reaction. There are several factors that affect the rate of reaction in the enzyme kinetics reaction. So what are those? The most important factors are the concentration of the enzyme itself, which are active. They might be an deactivated enzyme. So we only consider the concentration of active enzyme, and the substrates on inhibitors. The concentration. The temperature. And also pH. Temperature is very important here because of enzymes is composed by proteins. So in the condition with unsuitable temperature, the temperature might affect on the denaturation of the enzyme, which means that if you set if you set unsuitable temperature, what happens is the enzyme will damage. So reaction rates in the enzyme kinetics, we always refer to the initial reaction rates, where the maximum catalytic potential of the enzyme is expressed. So we are going to the highest catalytic value, reaction value, right? So there will be many factors that will affect this initial reaction rates, which are the substrate depletion, the accumulation of inhibitory product, the enzyme inactivation, and reverse reaction. In the enzymes kinetic reaction study, we need data. We need data in order to characterize the biocatalytic reaction. This schematic diagram, it summarizes the key data for the characterization of the biocatalytic reaction. So it means that from this schematic diagram, you may be able to know what are the data that you need in order for you to study the biocatalytic reaction. So in this topic, we are focusing on this part, the kinetic data. Alright, so the kinetic data, it will be on the kinetic parameter. We will identify how to get the value of the kinetic parameter, which are the maximum velocity or the maximum enzyme activity, the catalytic constant, K2, right? The catalytic constant, and the Km value, the Maclaurin-Menten constant value, right? And also, if for the inhibition study, so there is another constant there. It is called as inhibition constant, represented by Ki. In the enzyme kinetic reaction, there are two types of condition, which are the homogeneous enzyme kinetics and the heterogeneous enzyme kinetics. Okay, as we all know that homogeneous, it is where the reaction occur in the same phase. Okay, and heterogeneous, obviously it is in different phase. Okay, so for the homogeneous, okay, the catalyst, it will allow for a greater mixing and interaction, okay, between the enzyme and the substrate itself. Okay, so in this topic we are focusing on the homogeneous. Alright, so for the heterogeneous, I can give you example. Usually for this enzyme kinetic study, the example of heterogeneous is immobilized enzyme. So in the immobilized enzyme study, okay, you may come across with the entrapment or encapsulated enzymes, okay, in the matrix or in the material. So for the entrapment process of enzyme, you can use porous matrix to entrap your enzymes. Or for the encapsulated enzymes, immobilized enzyme, you can use a form of gel matrix in order to encapsulate your enzyme. But for this topic, we are focusing on this homogeneous enzyme kinetics. Okay, this is a simple enzyme mechanism. Okay, the general enzyme mechanism. Okay, reaction question and reaction equation. So in chemical mechanism, we know that the substrate, okay, it will produce product. Okay, substrate here means the reactant, right? So for the enzyme catalyst, right, we have substrate and we need enzyme in order to produce product. But there will be an intermediate here, which is called as reactive complex. Okay, so this reactive complex is this one, ES. Okay, enzymes, complex enzyme and substrate, where the enzymes bind to the substrate, okay, at this stage. And later you will have the product and the enzyme. So after the enzyme react with the substrate, okay, after the enzyme react with the substrate, it will produce a product here, and later the enzyme will release the product. Therefore, at the end of the reaction, you will have free enzyme and product. Okay, I would like you to focus here. Here, the equation 3.1. Okay, we have a free enzyme here. Okay, we have substrate, right? And here we have a constant rate. Okay, K1, K minus 1. Okay, in order to produce the ES complex. And later we have K2. Okay, the constants in order to rate constants in order to produce enzyme and product. Okay, in some book, okay, these rate constants, okay, for example here, this K1 and K2, right? Sometimes there is a book, there are books mentioned as K1, K2, okay, and here K2, okay, here K2, they will write as K3, okay, and some books it will write as what is presented here, K1, K minus 1 and K2. Okay, it doesn't matter in which form of K, okay, they are mentioned there in the books, but you have to know the location of that particular constants, okay, based on the reaction mechanism. Okay, this is the general reaction mechanism. Okay, so for K2 here, okay, K2 here, okay, this is where the K catalytic value. Okay, K2 is equals to the K cat value, K catalytic. Okay, there are two major approaches used in order to develop the rate expression of enzyme catalyst reactions. Okay, the first one is by using rapid equilibrium. Okay, so this rapid equilibrium, it is being proposed, okay, by Henry's, alright, which are Henry said that, okay, the conversion of substrate into product involve a reversible reaction between enzyme and substrate, okay, in order to break down delivering the product, in order to produce the product. Okay, this Maclist and Menton, okay, they have come up with the Maclist-Menton equation, and they also proposed the first formal hypothesis for the enzyme catalysis based on two sequential steps, as what has been suggested by Henry. So in the first step, the substrate is captured in the active site of the enzyme, and in the second step, the amino acid residues, okay, at that site chemically process the substrate in order to transform it into product. Okay, so equilibrium hypothesis, it was formulated based on the examination of hydrolytic reactions which in aqueous milieu are virtually irreversible. However, for reversible reaction, substrate turned into product, and then later product, it can be a substrate, okay, that hypothesis is not applicable and steady state equation must be derived. Okay, another approach is by using quasi-steady state, which is also known as PSSH, pseudo steady state hypothesis. Okay, it's similar. Alright, so a few years later, Briggs and Haldane, okay, argued against the validity of the rapid equilibrium hypothesis, and then they proposed the steady state hypothesis, according to which after a very short transient phase, the ES complex, enzyme substrate complex, remains constant throughout the whole reaction period, okay, which is represented by this figure here. Okay, throughout the period, here you can see here, it will be constant. Okay, so they propose for PSSH, okay, to be used in order in deriving the rate expression for the enzymatic reaction. Okay. So you can read in your textbook for further explanation on the derivation, and you can look at on the derivation shown in your textbook by using these two approaches in developing a rate expression of enzyme catalyst reaction. Okay, Maclist-Menton kinetics. Okay, this is where the kinetics start in order to identify the kinetics parameters involved in the enzyme kinetics reaction. Okay, so the Maclist-Menton equation, okay, it is shown here. This is the Maclist-Menton equation. Please do remember this equation, and this is the general equation, mechanism equation for the enzyme reaction. Okay, so the Maclist-Menton equation, okay, if you have a plot here, Maclist-Menton plot, okay, as it shows here, okay, this is the hyperbolic plot. Okay, you may able to find the Km value, the Maclist-Menton constant value, and the Vmax value from this plot.